Earlier we talked about rational numbers. The definition of rational numbers is any fraction where the top number is an integer, which is also called the numerator of the fraction, and the bottom number is also an integer, which is called the denominator of the function, so long as the bottom number is not 0. So 1 over 0 is not a rational number, but 0 over 1 is a rational number. As we talked about rational numbers, we said that actually we can express integers as rational numbers. For instance, 9 is the same thing as just 9 over 1. And an equivalent form for that is also 18 over 2. Because what we're seeing here is we're multiplying the 9 over 1 by 2 over 2 to get 18 over 2. Now, any number divided by itself, so long as those numbers are non-zero, has the value 1. So 2 over 2 is 1. And from our earlier example, we know that 1 is the multiplicative identity. So if you multiply by 1, you're not changing the value at all, which is why we can take this 9 over 1 times 2 over 2. Whenever we're multiplying fractions, it's always top number times top number, divided by bottom number times bottom number. So we would get 18 over 2 as an equivalent form of 9, and we could just continue this procedure. We could also say this is equal to 9 over 1 times the identity 1. Whenever you want to represent 1 as a fraction, it's always the same number divided by the same number. So for instance, we could see 3 over 3. Top times top is 27, divided by bottom, also 3. So any integer can be written as a rational number in this way, and what I hope we see from this as well is not only that there's at least one expression, there's actually infinitely many expressions, because 9 is also equal to 36 over 4. And so on and so forth. You could keep finding different rational expressions of 9. How could 0 be written as a rational number? Just as anything else, it's always 0 over 1, which is 0. Now, whenever we write 0 over 1 and we try to find other expressions by multiplying by what we might call our fancy 1, let's multiply it by 2 over 2. Top times top, 0 times 2 is 0, divided by 1 times 2, 2. But 0 divided by any number is always 0. Now, since there's all these equivalent forms of rational numbers, all of these are different ways that you could write the number 9, for instance. With fractions, there's multiple representations of the same idea. So what we need to be thinking about is how could we write something in lowest terms? It's lowest terms if the greatest common factor of the numerator, which is the number in the top, and the bottom number is factored out. So in this case, the greatest common factor would just be 1. They have nothing else in common other than the integer 1. The way this is written is this is actually called the fundamental property of rational numbers. Don't worry about the name, but that's just what it's called. And that's the idea that any number a times b can be simplified if they have some integer in common, where we've got a times b multiplied by k over k. That's our idea of the fancy 1, like what we wrote over here. A times b times k over k still takes on the value of a times b. Now, if we're asked to write numbers in lowest terms, we need to make sure we factor out any greatest common factor. And one way that you can think about this is, first, do we see that both of these numbers end in an even number? That means they're both divisible by 2. So we could say 36 over 52, well, that's equal to 18 times 2, because in our calculator we could say 36 divided by 2 is 18. 52 divided by 2 is 26 times 2. And what happens is this 2 over 2 is coordinating to be the value of 1, or you could imagine that since it's the same above and below through multiplication, they cancel out. And we get this fraction is equivalent to 18 over 26. But again, since both these values end in an even number, we know they're divisible by 2. So we could rewrite this as 18 divided by 2 is 9, so 9 times 2. 26 divided by 2 is 13, so 13 times 2. These are equivalent. 18 is 9 times 2, 26 is 13 times 2. Cancel what they have in common. This simplifies to 9 over 13, and then we think to ourselves, do 9 and 13 have anything else in common? I would say no, so their greatest common factor between 9 and 13 is 1. This means it's in lowest terms. I recommend you pause and through a similar way, and you could jump immediately from here to here if you factor out higher powers as well. Don't feel like you need to do it step by step by step if you see something that you could take out that's a larger value. Pause the video and work on our next example. When you finish working on it, unpause. We recognize both 24 and 16 are even numbers. That means they're both divisible by 2. 24 is 12 times 2. 16 is 8 times 2. The common 2's would cancel, leaving us with the equivalent fraction 8 divided by 12. Now at this point you could say, well, 12 is divisible by 2, so is 8, and you could continue it as we've been doing. But this is an example where you could actually factor out more than just a 2. We know 4 times 3 is 12, 4 times 2 is 8. So why not rewrite this as multiples of 4? 3 times 4 gives us 12, 2 times 4 gives us 8. The common 4's cancel, and it simplifies to the fraction in lowest terms of 3/2 or 1.5. Now the reason we like to express fractions in lowest terms is because if a fraction's in lowest terms, we can immediately identify if it's the same value. But when fractions aren't written in lowest terms, we don't necessarily know, without use of a calculator off the top of our head, are these fractions representing the same numerical value? And this is why this test for seeing when fractions are equal can be very useful. So if we had two fractions, 15, is it equal to 5/4? Well, our rule is called the cross product test, and what it's saying is two fractions are equal only if you could multiply a times d and it would be equal to the value b times c. So let's set that up. We would say 15/12 is equal, and I'm going to put a question mark here because we don't yet know. We don't want to make a statement that they're equal yet. Is equal to 5/4 if 5 times 4, this is the idea of if and only if both directions have to be true, needs to be equal to 12 times 5. With our calculator, we would calculate each one. 5 times 4 is, sorry, I wrote this wrong. It's 15 times 4, top times this bottom, which would be 60, is definitely equal to 12 times 5, which is also 60. So since this is equal, then we know the fractions are equal, and definitely 15/12 is just another expression of 5/4. And in this case, 5/4 is now in lowest terms. So this will be useful if you're given two fractions and you're asked if they're equal without the benefit of a calculator. Now, of course, if we have a calculator, another way you could do this is you would just type both fractions into your calculator and see if you get the exact same decimal representation. But that does come into the issue of, are you just getting that they're the exact same for the values that you see on the screen? There could be more decimal places coming later. And we'll see how to deal with that in a second. For the next few minutes, we are actually going to be reviewing adding, subtracting, multiplying, and dividing fractions. If this is something that you're extremely confident with, I recommend you work a few of the problems, go ahead to where I have the solutions, make sure they're correct, and then if you want, you can then go on to the application problems that are going to come later. But if you would like a refresher on how to add, multiply, divide, or subtract, we're going to be doing that here, and we'll go through some detailed examples. Now, whenever you're adding or subtracting rational numbers, you can't just add any two fractions. For instance, well, you can, but you can't immediately do it. I can't immediately add 1/2 plus 3/4. I can eventually add them, but what's got to happen is the denominators, that's the numbers in the bottom, have to be the same, because fractions are really representing parts of wholes, and you can only add parts of wholes if they're out of the same whole amount. That brings to the idea of the least common denominator. The least common denominator is the way that we could get the denominator values to match, and the way we're going to do that is by use of our fancy 1. Because of the identity property, we know 2/2 is 1. That's just one example. Any number over itself is 1. You can always multiply by 1 and you're not changing the value. The reason this is beneficial is whenever we say things are equal, we really mean this side is literally equal in weight to the other. So we don't want to multiply by anything that would offset that balance. That's why multiplying by 1 is a great option. As we're looking to add 2/15 plus 1/10, we can't immediately add them because their denominators are not the same. 15 does not equal 10. Now we need to think about how can we manipulate those denominators to be the same value while not changing the overall expression. That's the idea of the least common denominator. For instance, 15 divides 30. 15 times 2 is 30. 10 divides 30. 10 times 3 is 30. So we've got that. If you rewrote this, and this is just a helpful way I recommend rewriting it, give yourself a lot of space. Notice I'm rewriting the fractions. There's a lot of space next to it, and I'm going to be multiplying by the quote-unquote fancy 1. I know that my least common denominator for these between 15 and 10 is 30. So you have to ask yourself, 15 times what gives you 30? Because remember, with multiplication of fractions, top times top, bottom times bottom, that would be 2. But what goes on the top, or the bottom, has to go on the top so that this is really the value 1. Okay. Then you ask yourself, 10 times what gives you 30? That would be 3. So since there's a 3 in the bottom, there also has to be the 3 in the top, because 3 divided by 3 is also 1, and multiplying by 1 doesn't change the value. So all we're doing is manipulating the way it's expressed, but the value is the same. Now we multiply fractions. 2 times 2 is 4, divided by 15 times 2, which is 30, so 4/30, plus 3/30. And now that the bottom number or denominator is the exact same value, we can immediately add. And the way that you add fractions is you keep the same denominator, so we just immediately rewrite 30, and then you just take 4 plus 3, which would give us 7. Next, let's turn our attention to subtracting fractions. Now, the idea is the same. You can only subtract fractions if the denominators are the same. Giving this one a quick glance, we see one has a denominator of 180, the other has a denominator of 30, so they're not the same. But since 30 is significantly smaller than 180, and they kind of look like they might be divisible by each other, let's just check in our calculators. If 180 can be divided by 30, then we've got an easier least common denominator. So for instance, 180 divided by 30 in my calculator is 6. So that tells me I've only got to manipulate this fraction. If I multiplied it by 6/6, which is a fancy 1, this denominator would now be 180, and I could subtract the two fractions. So we keep the first one the same, it's not changing, but we're going to rewrite it in an equivalent expression. 12 times 6 is 72, divided by 30 times 6 we know is 180. Now the denominators are the same number, so we can actually subtract these. So we would get the way you would subtract fractions. Again, remember with subtraction, order of subtraction matters. So you want to be cautious here. You always write the same bottom number below, and then you take this minus this. So 173 minus 72. Remember, you are allowed a calculator in this class, so it can help you with these quick operations, and we would get 101 divided by 180. Now, within the course of this lecture, we already reviewed multiplying fractions. Remember, it's top times top divided by bottom times bottom. So whenever we're looking at 3/5 times 8/10, we don't even have to worry about getting the same denominator. That's only with addition and subtraction. We would just say top times top, 3 times 8 is 24, divided by 5 times 10, 50. Similarly, our next one, 6 times 3 is 18, divided by 4 times 4, which is 16. Now, with division, we're always asking ourselves how many of this one unit that we're measuring can fit inside of another unit of measurement. Specifically, if we've got 7/8 gallons of milk, we'd want to know how many quarts we have. Now, a quart is always 1/4 of a gallon, so we don't yet have a full gallon of milk. So we don't have exactly 4 quarts because it's 7/8. But we know it's going to be a little less than 4 quarts because 4 1/4 would be exactly 1. 7/8 is very close to the fraction 1. So we've kind of got that estimation in our mind, but if we wanted to find the answer exactly, what this is asking us is how many 1/4 as a fraction are in the fraction 7/8, which is the phrasing of division. This is the same as 7/8 divided by 1/4, and as we talked about earlier, remember order of division matters. 1/2 is different than 2/1, so we'd really want to watch this order. It's 7/8 divided by 1/4, which could be rewritten as the top fraction divided by the bottom fraction. Now, whenever you're dividing fractions, there's this neat mnemonic device of keep it, change it, and flip it. And this is the idea that you keep the first fraction as is, so 7/8. You change the operation from division to its opposite, multiplication. You could write it by the x bar, like the x multiplication, or just the dot multiplication. And then you flip the bottom fraction. So what was 1/4, we now flip it completely, and it would be 4/1. With this, we can think of fraction division under keep it, change it, flip it. And the nice thing is multiplying fractions is the easiest operation we can do with fractions because it's the top number times the top number divided by the bottom number times the bottom number. So the final result is 7 times 4, which is going to give us 28, divided by 8 times 1, which gives us exactly 8. So the amount of quarts that we have is 28/8 quarts. And if we wanted to look at that as a decimal, that would be exactly 3.5 quarts. So very close to what we thought, less than 4, but exactly how much less? 0.5 quarts less. Now we just have a bit more practice with fraction division. If you're kind of getting familiar with this idea, I recommend that you would pause the video now and work on these 3 problems separately. Then when you're ready, unpause the video and check your work, and we'll go through the solution together. When we're dividing fractions, we'll want to keep the keep it, change it, flip it close in our mind. So we keep the first fraction, we change the sign to multiplication, and then we flip the second fraction, and then it's fraction multiplication, so top times top would give us 30, divided by bottom times bottom would give us 35. On to the next problem, keep it, change it, flip it. Keep the first fraction, we see this is a -4. Change the sign, flip the next fraction, and that would give us top times top divided by bottom times bottom, -56/27. Now, our next one doesn't necessarily look like a fraction, but fraction division still works, because remember, every integer can be expressed as a rational number, specifically in infinitely many ways, but the most simplest way to express an integer as a rational number is just to divide it by 1. So we could rephrase this as -9 divided by 1 divided by 5 divided by 9, because we haven't changed the value at all, it's just an equivalent expression. By keep it, change it, flip it, we would keep the first fraction, change the sign, flip the second fraction, and we would get -81/5 as our final answer there. Now in this next example, we've got a problem involving fractions, and we need to think about, just by the way it's worded, what operation are we looking to figure out. So it says a carpenter has a board that is 72 inches long, and he must cut it into 10 pieces of equal length. This will require 7 cuts. Now, what's going to happen is if each cut, whenever you cut the board, suppose that there's 3/16 of waste. So we know when we cut the board, we don't have the exact equal amount from the right and the left, because through the saw, we lost a bit of the portion of the board, specifically 3/16 of an inch. How many inches of actual board will remain after the cuts? Now nicely, they told us that we were actually going to have 9 cuts. So every time we cut the board, we lose 3/16 of an inch. So we could think about adding 3/16 9 times. So 3/16 plus 3/16 plus 3/16 on 9 times, but that's going to be tedious. But what we recognize there is that's repeated addition. Repeated addition is the same thing as multiplication. If you add 3/16 to itself 9 times, that's the same as multiplying 3/16 by 9. And to help us see this as fraction multiplication, we can rewrite 9 as 9/1. And we would get this is equal to top times top is 27/16. So we've got 27/16 inches that are going to be wasted from our cutting. Now, we didn't ask how much was wasted, we asked how much is remaining. So to finish this problem, we've got to go back to, well, how much did we start with? And that was 72. And how much did we lose? 27 over 16. So now we've got to rephrase this in terms of subtracting fractions. Currently, 72 could be expressed as over 1. So what we would need to do is get a least common denominator. And specifically, if you just multiply this fraction by 16 over 16, we would get the least common denominator of 16 here. Remember, multiplying by a number divided by itself is not changing the value because this is really the value 1. 1 times anything stays 1. But we would get that 16 multiplied by 72 is 1,152. All divided by 16, we're subtracting 27 over 16. Whenever you're subtracting fractions, it's this minus this with the same denominator. And we would get 125 over 16 inches remain. $1,125 over 16 inches remain after the cuts. Our next question asks us, after we found these 10 equal pieces, what is the length of each of these resulting pieces? Now, as we're thinking about this problem, what's going on is we've got to think of how much board do we have left. We've got 125 divided by 16 inches of board left to work with after the cuts are made. We are going to have 10 different pieces of board that fill up this total amount of material. So 10 pieces, 10 equal pieces, come from the original amount that was left over of the 125 over 16. This is the idea of division. This is telling us 125 divided by 16 divided by 10 would be how much? If we're going to divide this amount that we've got into 10 equal pieces, we would need to do that. Now, we could help ourselves by seeing this as fraction division, as 10 over 1. Remembering we keep the first, change the sign, flip the second, and then we've got 1,125 divided by 160. And if we want to do that in our calculator, that would get us exactly, we'll say it's about 7.03125 inches long. So each piece of board would have to be about 7.03125 inches, and we'll have 10 of those. That would make up our original piece minus the cut difference. A really interesting thing to think about when it comes to rational numbers that's quite different from the integers is that there is infinitely many rational numbers in between any two rational numbers that you pick, which is not the same for integers. For instance, if I start with like 3 and 5, and I ask you what are the integers between 3 and 5, we would know the only integer that lives between 3 and 5 is 4. But if we ask, well, what are the rational numbers that are between 1/2 and 3/4, there's actually infinitely many rational numbers that are between 1/2 and 3/4. This is the idea of the density of rational numbers, and maybe I'll start with easier ones to think about. We know 0 over 1 is a rational number. 1/2 is a rational number. On the number line, we'd have 0, 1/2. Thinking about why there's infinitely many rational numbers here, we might first think about, well, we could divide this number line distance into half. So half of 1/2 is 1/4. And that's a rational number between 0 and 1/2. But we could do that again. We could divide now this distance by half. Dividing that distance by half would give us 1/8. And if we just keep dividing by halves, there's always a distance that's positive. So you can always divide a positive distance by half and get a smaller distance. So you can do this infinitely many times, where the next half would be 1/16. Now I'm running out of space here, but if you could imagine zooming in, then the next half would be 1/32, and at some point my computer can't zoom in any further, but theoretically you could keep doing that. 1/64, 1 over 28, 1 over 256, on and on and on. So just from that brief example, we can see why it makes sense that between 0 and 1/2 there's infinitely many rational numbers. But that doesn't even take into account, for instance, 1/3, which lies between 1/4 and 1/2. So just from that one string of argument of just keep halving the distance between 1/2 and 0, you would get infinitely many rational numbers. We see there's even more than that because there's values like 1/3 in between that don't even just fit that category. Whereas if we were looking strictly at integers and we started at 3 and we were at 10, there's only finitely many integers that lie between 3 and 10. For instance, 4, 5, 6, 7, 8, 9. But between any two rational numbers, or fractions, there's actually infinitely many other rational numbers that lie between those two values. This is the idea of the density. So since that for between any two rational numbers, there's actually infinitely many rational numbers, we call the set of rational numbers dense. We also call the real numbers dense, but we do not call the integers dense because there's only finitely many integers between any two integers. Now, our next example goes over the idea of average cost, which comes up with the idea of you can add certain values and then find the average dividing by how many values you added together. So we've got a table that shows the amount of tuition and fees at a private four-year institution for 5 years. So during academic year 2007-2008, all the way down to 2011 and 2012, we can see that for this way, the way we'd read the table is during this academic year, this is the amount of tuition and fees. This is the next one, and so on and so forth. And we're asked specifically about the average cost. Now, since this table is the cost, we're just asking to find the average of this table. So with average, you would always add all the values and then divide by how many values you counted. So there's 1, 2, 3, 4, 5. So we are going to add all the values and then divide by 5. Here we'll want our calculator, 21,427 plus 22,036 plus 22,771 plus 23,479. And just to show that all of this is being divided by 5, I might offset this in parentheses, which means do the addition first and then divide by 5. Let's simplify the numerator or the sum from the top. And we would get 100,000, 111,621. We're going to divide that by 5 using our calculator. And we would get that the average cost over this 5-year period of time is $22,324.20, and that would be per academic year. Now, the decimal system is based on powers of 10. So if we've got a decimal point here and we're looking at the number 483.039475, we would call that 400. 8 times 10 is 80, so 483, that's how we'd represent that. 483.039475, and then we would call the 0 as the tenths place, the 3 as the hundredths place, so we'd say point, and then the thousands, 10,000s, 100,000s, and millions. And what we'd want to recognize is for each of these moves in a place, so if we go from the left of the decimal place over by 1, you've got to multiply by 10, multiply by 10, multiply by 10. Similarly, as we go to the right of the decimal place, we still keep multiplying by 10s. So if it says round to the thousandths place, let's say that, round this number to the thousandths place, that's another way for saying, okay, this is the tenths, the hundredths, the thousandths. That's another way of saying round to 3 decimal places. And the way that we would look about rounding is you would look at the digit to the right of the place that you want to round to. If it's 5 or greater, round up. If it's less than 5, stay the same. This is 4 less than 5, so it would stay the same. So rounding this to 3 decimal places or to the thousandths place would be 483.039. Now, with all these rational numbers are real numbers. And the definition of real number is that it can be expressed as a decimal. So definitely all these fractions have decimal representations. Some of them we're more familiar with than others. 1/4 we were familiar with to be 0.25 or a quarter. Now 89 over 10,000, the way we would think about that is the 89 has the decimal place here, right after the 9. And if we're dividing by 10,000s, it's like we're moving the decimal place over 4 positions to get to the 10,000ths. So 1, 2, 3, 4. So what we need to do is we need to move the decimal place 4 places to the left. It should be getting smaller. Number divided by much bigger number is a smaller number. And everywhere where there's not a 0, we'll add it here. And we would get this is equal to the decimal representation of 0.0089. Now, in our calculator, we could evaluate the next one to be 0.3875. But if we wanted to work through this without a calculator, we could do it similarly as well. I'll just go over that really quickly. If we weren't using a calculator, which we could use a calculator to solve this as we just did, the way that we think about it otherwise is we know how thousands dividing by thousands works because that's with the decimal place that we're used to. So I would first rephrase this as 2 times 1,000, that's what 2,000 is, dividing into 775. We can split this apart to 1/2 times 775 over 1,000. This we can calculate it using a similar principle. 775 currently has a decimal place there. We want to move it over to the thousandths place. That's 1 movement, 2 movements, 3 movements. So that's going to be 1/2 times 0.123.775. 1/2 times 0.775 would give us our 0.387.75. Finally, our next one, we could go through some similar procedures, or we can just use our calculator. 25 divided by 16 is 1.5625. Now, one of the reasons that we are going over this is just to get familiar with how the decimal position system works, but also to recognize that each of these decimals has a clear ending point. They don't keep going on forever and ever and ever. This is the idea of a terminating decimal. A terminating decimal is a decimal that eventually stops. Now, it could go on for 10,000 decimal places, but as long as it's stopped at some point, it's terminating. And that's the tricky thing, because in our calculator, we might be doing well if we get 15 decimal places represented before the screen cuts off. So just because on your calculator it looks like the number ends, you don't necessarily know if it's ending or if the calculator is just running out of space to show you all the decimal places. This brings us to the idea of when is a decimal called a repeating decimal. So if a number continues indefinitely with some pattern, it's called a repeating decimal. Some well-known repeating decimals are these. First, 1/3 is 0.333, continuing on forever. The way you could represent that is you could either do the ... to indicate that it keeps repeating 3s, or more commonly, you would use a line over the top. That means it keeps repeating the 3. So 0.33333 forever and ever without stopping. Let's express the other decimals, find them in our calculator. They are also 5/11 is 0.45454545, and it's a repeating decimal. So what's happening is the 4/5 just keeps repeating. So if we were going to express this with the line notation, we would need to make sure that we draw the line over the entire 4/5, because that shows the 4/5 pair keeps repeating. If it was 0.45 and then a line, that would be 0.4 and then 5s forever and ever. So if you want the entire pattern to repeat, you draw the line over the entire repeating pattern. Now, 5/6 is 0.8333. So in this case, what's repeating is the 3 continues forever. So to represent that, we would say 0.83, and the line is just going over the 3 to show that that's what repeats to infinity. Now, any rational number is either going to be a terminating or a repeating decimal. Since we know that every rational number must fit one of these two categories, it would be helpful for us if we had a rule to know when is a fraction going to be repeating and when is it going to be terminating. Because we can't just trust our screen because we don't know if the fraction ends or if the fraction just calculator runs out of space to show us what's going on. To know this rule, we need to know about some prime numbers. Our quick introduction of prime numbers is that the lowest prime numbers are 2, 3, 5, 7, 11, 13, 17, 23, 29, and there's actually infinitely many more prime numbers, but we're just going to care about these for now. A rational number, a over b, so that's top number divided by bottom number, in lowest terms, so we first have to get the fraction into lowest terms first, is terminating if there's only prime factors of the denominator. The only prime factors of the denominator are 2 or 5 or both. So you could have a 2 and a 5. A rational number in lowest terms is repeating if there's a prime other than the 2 or 5 in the lowest form of the denominator. Let's go through some examples of this. So based on the above criteria, we need to understand if these are going to be terminating or repeating decimals. We know that in both cases, you've got to look at the lowest form of the fraction. So let's first consider are each of these fractions in lowest form. Once we simplify them if necessary, then we'll start applying our criteria from above. 7 and 8 have nothing in common than 1 as a common multiple, so it's in lowest terms. We can start evaluating it. Let's think about 13 and 150. 13 is actually a prime number. So a prime number has nothing in common with another number other than 1, so it's also in lowest terms. But our next one, 6 divided by 75, they both have 3 in common. For instance, 6 is 2 times 3, 75 is 25 times 3. If we cancel the common term, we would get 2 over 25, and now that is in lowest terms. So the next property is you've got to factor the denominator into the prime factors. So in this case, we've got 8. So to find the prime factors, you can make a factor tree. 8 can be divided by 2 and 4. 4 can be divided by 2 and 2. And when you get down to all prime numbers and 2 is a prime number, that's when you know to stop the factor tree. And all the digits at the bottom of the tree are your prime factors. So this is saying 7/8 is 7 over 2 times 2 times 2. Now, there is only factors of 2 here. So looking back at our criteria, we've only got prime factors of 2 or 5 or both. In this case, it's just 2. So our original first example is going to be a terminating decimal. And if we wanted to just clarify this, we could also type 7 divided by 8 in our calculator. And notice that check only helps us to know if it's clearly terminating. We can't know if it's repeating just from that because we don't know if the calculator is just not showing more of the digits or if that's all there is. But we at least know since this is exactly equal to 0.875, it clearly ends after the 5. Now with our next one, we'll make another factor tree because we want to know the prime factors of the denominator, the bottom number, if the fraction's in lowest terms. There's many ways to make the factor tree. In the end, you'll still get the same number as long as you carry the factor tree through all the prime numbers. But I first see that it's 150. It ends in a 0, so that means it's divisible by 2. In your calculator, you could do 150 divided by 2 and you would get 75. Now 75, I might recall that it's divisible by 25, so it's 25 times 3. Now 2 is a prime number, 3 is a prime number, so we don't have to go any farther with those strands of the tree, but 25 is not prime. For instance, it's 5 times 5, so we factor that. And now we've got only prime numbers, 2s, 3s, 5s, those are some of the first few prime numbers. This is telling us that 13 over 150 could equivalently be expressed as 13 divided by 2 times 3 times 5 times 5. And if you want to verify that 2 times 3 times 5 times 5 actually would give you 150, this is the prime factorization. And we see that we've got primes 2, 3, and 5 in the denominator. Let's go back to our rules to see if this would make it a terminating or repeating decimal. Notice we had the prime number 3. So we had a prime number other than 2 or 5. So that would make the fraction we were just working with a repeating decimal because the prime number 3 was present in the denominator. So 13 over 150 is a repeating decimal. And this is something that if we just typed it into our calculator, we couldn't be sure about because we don't know, does it end after the last digit portrayed or does it just continue in a pattern? But now we can know for sure that it repeats forever in the pattern that was set. Okay. If we wanted to type this into our calculator, 13 divided by 150, we would get 0.08, and then it looks like the 6 keep repeating. So if we were writing this with our notation, the bar would be over the 6 to show that it's the 66666 after the 0.8. Let's go to our final example. Now with our final example, we do want to be cautious because these two properties only apply if the fraction's in lowest terms. So we first recognize that 6 over 75 wasn't in lowest terms, but 2 over 25 is in lowest terms. So now we would find the factor tree of the denominator. So we're no longer looking at 75 as our factor tree because it's the fraction in lowest terms that you do the factoring of the denominator. So we would say 25 has factors 5 and 5. Those are the prime factors. This is the same as 2 divided by 5 times 5. Since the only prime numbers in the denominator are 2 or 5, we know that this would make our fraction a terminating decimal. Specifically, typing this into our calculator, we would get that it is 0.08. And this is my word of caution why you had to first get it into lowest terms. If you try to factor this denominator, we know that's 3 times 25. There would be a 3 appearing as the prime factor, which would make us think it's a repeating decimal, but if we just type it into our calculator, we clearly see it's a terminating decimal. So remember, these rules only work if you're looking at the denominator of the lowest form version of the fraction. So you first have to get it to lowest terms, and only then can you apply the factor tree method to see if it's a terminating or repeating decimal. And that brings us to the end of this section's notes. Thank you.